Welcome everyone. In this part, I will discuss about oscillations in an electrical circuit. In my previous lecture, I discussed about simple harmonic motion of the mechanical system. In this lecture, we will see that these oscillations, that is the oscillations of an electrical circuit, are described by differential equation that is identical in the form to the differential equation of simple harmonic motion for the mechanical system. So the solution will be identical. Only the physical quantities associated with the differential equations are different. That means when we understand one physical situation, we can understand many others. So you can think that we can simulate one system by another, and actually in this way you can build analog computers. That is, you can build an electrical circuit having resistors, capacitors and inductors that will exactly simulate the operation of a mechanical system. This figure shows an electrical oscillator consisting of an inductor L and a capacitor C connected in series. So when a capacitor is connected to an inductor, the combination is an LC circuit. As I have explained in the previous lecture, we start with an idealized situation. That means we consider that the resistance in the circuit is zero. If you think about the mechanical system, this is analogous to the assumption that there is no frictional forces present in the mechanical system. Now, coming back to this LC circuit, initially the switch is open and the capacitor is charged to a voltage V. The charge Q on the capacitor is equals to V into C, where C is the capacitance. Now, if we close the circuit, that is, if we close the switch and the charge begins to flow through the circuit, that is through the inductor, and the current is equals to I is equals to dq by dt flows in the circuit. This time varying current produces a voltage across the inductor, and this is equals to L di by dt. Now, using Kirchhoff's law, we can analyze this LC circuit. So according to Kirchhoff's law, the sum of the voltages around the circuit is equals to 0. So that means voltage across the capacitor plus voltage across the inductor is equals to 0. So the equation of voltage due to the instantaneous current I can be written as Q by C plus L di by dt is equals to 0. Now you know that I is equals to dq by dt, so we can rewrite this equation and we can say that Q by C plus L into d2q by dt2 is equals to 0. So we can write this as d2q by dt2 is equals to minus 1 by L into C into Q. So now if we consider that 1 by L into C is actually equals to omega square, so it is of the same form as for the case of mechanical system, that is for the spring oscillator case or for the pendulum, and represent simple harmonic motion. So we have the initial condition, that is that t is equals to 0, the charge on the capacitor has its maximum value. Then the solution to this equation is Q is equals to Q max into cos omega t plus phi, where Q max is the initial charge on the capacitor. Now, if we want to know the energy in this electrical oscillator, that is in this LC circuit, you know that for a mechanical system, that is for the pendulum or for a spring mass system, the total energy is equals to kinetic energy plus potential energy. Now the potential energy, that is equals to half kx square stored in a stretched spring, is analogous to the electric potential energy, that is equals to half cv square stored in the capacitor, and the kinetic energy, that is half mv square of the moving block, is analogous to the magnetic energy half li square stored in the inductor. And this actually requires the presence of moving charges. So now you can say that the total energy in this LC circuit is equals to half Li square plus half Cv square. And you know that V is equals to Q by C, so we can rewrite this expression for the energy, and we can say that total energy in this LC circuit is equals to half Li square plus Q square by 2C. And assuming that the circuit resistance to be 0, so no energy is transformed to internal energy and none is transferred out of the system to the circuit. Therefore the total energy of the system must remain constant in time. So we can say that the first derivative of the total energy with respect to time is equals to 0. So that means d by dt of this total energy, that is half Li square plus Q square by 2C, is equals to 0. So we can rewrite this expression and we can say that Q by C into dQ by dt plus Li into di by dt is equals to 0. So that means an LC circuit oscillating at its natural resonant frequency can store electrical energy. So you can see this animation. A capacitor stores energy in the electric field between its plates, depending on the voltage across it, and an inductor stores energy in its magnetic field depending on the current through it. If an inductor is connected across a charged capacitor, the voltage across the capacitor will drive a current through the inductor, building up a magnetic field around it. The voltage across the capacitor falls to 0 as the charge is used up by the current flow. At this point, the energy stored in the coil's magnetic field induces a voltage across the coil. This induced voltage causes a current to begin to recharge the capacitor with a voltage of opposite polarity to its original charge. Now, due to Faraday's law, the EMF, that is the electromotive force which drives the current, is caused by a decrease in the magnetic field. Therefore, the energy required to charge the capacitor is extracted from the magnetic field. When the magnetic field is completely dissipated, the current will stop and the charge will again be stored in the capacitor, with of course the opposite polarity as before. Then the cycle will begin again with the current flowing in the opposite direction through the inductor. The charge flows back and forth between the plates of the capacitor through the inductor. The energy oscillates back and forth between the capacitor and the inductor until internal resistance makes the oscillations die out. The tuned circuit's action, known mathematically as a harmonic oscillator, is similar to a mechanical harmonic oscillator. For instance, you can think about a pendulum swinging back and forth. So now we will talk about an important phenomena that is called resonance. Resonance occurs when a LC circuit is driven from an external source at an angular frequency omega 0, at which the inductive and the capacitive reactances are equal in magnitude. That means omega L is equals to 1 by omega C. The frequency at which this equality holds for a particular circuit is called the resonant frequency. The resonance effect of the LC circuit has many important applications in signal processing or in the communication systems. For instance, tuning radio transmitters and receivers. So when you actually tune a radio to a particular station, the LC circuits are set at resonance for that particular carrier frequency. Also, a series resonant circuit provides voltage magnification. A parallel resonant circuit provides current magnification. And this resonant frequency of the LC circuit, that is, we can express it or we can represent it as omega 0, and this is equals to root over 1 by L into C, where L is the inductance in henries and C is the capacitance in farads, and the angular frequency omega 0 has units of radians per second. Nevertheless, if you want to get the equivalent frequency in units of hertz, it is simply the omega 0 by 2 pi, and that is equals to 1 by 2 pi into root over L into C. So now we are going to compare this electrical oscillator with the spring mass systems, which is actually an example of a mechanical harmonic oscillator. So we have the initial condition, that is at t is equals to 0, the charge on the capacitor has its maximum value, that is Q is equals to Q max. No current is flowing in the circuit, so no energy contribution from the inductor. This is actually equivalent to the expanded spring mass system where V is equals to 0 and the energy is all potential. Now voltage across the capacitor will drive a current through the inductor, building up a magnetic field around it. After a quarter of a cycle, the voltage across the capacitor falls to 0 as the charge is used up by the current flow. And here the energy is all inductor's contribution. This is actually equivalent to the equilibrium position of the spring mass system, where the velocity has its maximum value and the energy is all kinetic. So now the energy is stored in the coil's magnetic field, induces a voltage across the coil. This induced voltage causes a current to begin to recharge the capacitor with a voltage of opposite polarity to its original charge. So when t is equals to t by 2, that is after a half of the cycle, the charge on the capacitor again will have its maximum value, that is q is equals to q maximum. No current is flowing in the circuit, so no energy contribution from the inductor, and this is actually equivalent to the compressed spring mass system. Now the question is, why equivalent to the compressed spring mass system? Because of the opposite polarity. So here this graph shows the variation of the charge and the current with time. You can see here that at t is equals to 0, the charge on the capacitor has its maximum value, that is q is equals to q max. So no current is flowing in the circuit, so I is equals to 0 at this point. After a quarter of the cycle, that is here, voltage across the capacitor falls to 0 as the charge is used up by the current flow. So maximum current at this point. Again at t is equals to t by 2, that is after a half of the cycle, charge on the capacitor will be maximum but with opposite polarity, and the current in the circuit will be 0 again. So we can say that the total energy is constant, so half Li maximum square is equals to Q maximum square by 2C. So this is the energy contribution from the inductor and this is the energy contribution from the capacitor. So now after T, that is T is equals to T, that is when you complete a cycle, when the magnetic field is completely dissipated, the current will stop and the charge will again be stored in the capacitor with the opposite polarity as before. And this is actually equivalent to the expanded spring mass system where V is equals to 0 and again the energy is all potential. Now these two figures represents the variation of energies with time. The red one is energy stored in the inductor and the yellow one is the energy stored in the capacitor. So at t is equals to 0, as q is equals to q max, so there is no current in the circuit, so the magnetic energy stored in the inductor will be 0 and the electric potential energy stored in the capacitance has its maximum value, that is q max square divided by 2c. After a quarter of the cycle, the voltage across the capacitor falls to 0 as the charge is used up by the current flow and I will be I maximum. So the energy stored from the capacitance will be 0 and the magnetic energy stored in the inductor will be maximum, that is half Li maximum square. So now if you think that we have somewhere here, or you can say we are somewhere at this point where we have both the contribution of electric potential energy and the magnetic energy stored in the inductor, so we can write that U is equals to, that is the total energy is equals to half Li square plus Q square by 2C, and Q is equals to, you know, that is Q max into cos omega t, so I will be Q max into omega sine omega t. So now if you replace Q and I in this equation of the total energy, you can get that U is equals to half L into Q max into omega sine omega t whole square plus Q max cos omega t whole square by 2C, and you know that omega is equals to 1 by root over L into C. So by replacing this omega with this 1 by root over L into C, you can get that U, that is the total energy, will be equals to Q max square divided by 2C into sine square omega t plus cos square omega t, and you know that sine square omega t plus cos square omega t is equals to 1. So the total energy will be equals to Q max square divided by 2C, so that means the energy is constant. Now to summarize, here I have discussed the oscillations in an electrical circuit. We saw that these oscillations, that is the oscillations in an electrical circuit, are represented by a differential equation that is identical to the differential equation of simple harmonic motion for the mechanical system, that is for a spring mass system or a simple pendulum. So the solution is actually identical, only the physical quantities associated with the differential equation are different. And for this electrical oscillator, the energy contribution is from the electric potential energy stored in the capacitor and the magnetic energy, that is half Li square, stored in the inductor. And as there is no resistance, that is there is no internal resistance, the total energy of the system is constant with time. So that's all for today, and in the next class I will discuss about damped oscillations and the forced oscillations.